Welcome back to the next Demystifying Blockchain session, where today we'll talk about HyperLedger, and Sam will go into more detail about the architecture, the performance, and security aspects. Over to you, Sam.
Thank you, Julia. So as Julia said, we will be diving into some of the technical and architectural details of the HyperLedger Fabric permissioned blockchain software solution. So just a brief background. So HyperLedger is a consortium that a number of organizations have donated open source code to. HyperLedger Fabric is one project as part of that consortium that was primarily led by IBM. IBM had an internal project called Open Blockchain, which they open sourced and donated to the HyperLedger consortium. And since this was around very late 2015 or very early 2016, since then, HyperLedger Fabric has become a Linux Foundation project, which with contributors all over the world, from not just IBM, but other large companies like Fujitsu, London Stock Exchange Group, State Street Bank, and of course an assortment of startups. And so it's got a huge amount of development and interest globally building on top of this project. As we talked about in the previous session, HyperLedger Fabric is a general purpose smart contract execution platform, meaning just like how a CPU can execute arbitrary computer programs, HyperLedger Fabric can be programmed and used in a variety of different settings, including financial settings, but not just financial. And that philosophy has influenced the architecture and a lot of the design decisions, which we'll dive into today. So I should mention that the architecture and the details that we're talking about today are the most recent version of HyperLedger Fabric. So HyperLedger Fabric is currently on 1.2. There was a huge architectural change between 0.6, which is mainly based on this open blockchain initiative that was internal to IBM, to 1.2. So sometimes it can be confusing because the architectures are very different. So in the latest version of HyperLedger Fabric, they have adopted a new type of blockchain architecture called an execute order validate EOV architecture. And this is different. This has to do with the transaction lifecycle. So the day in the life of a transaction, how it gets executed, ordered, and validated, which we'll talk about. But it's very different than almost all the other blockchain architectures, which use an order execute type of architecture. So briefly, if you recall in our other descriptions and our other sessions when we talked about blockchain architectures, there would be, like for example, Bitcoin, where you would have a client that creates a transaction. That transaction gets broadcast to the network. Miners will collect those transactions and group them into a block. And once the miner has found a valid block, they'll broadcast the block to the network. And then that's the ordering. So the block, the order of the blocks and the chain of the blocks forms a total order of all the transactions. So you use the block with the largest height or the greatest amount of work behind it in the Bitcoin network. This is the proof of work consensus protocol. And the miners, when they group these transactions into the blocks, by doing that, they're establishing a total order of all the transactions. So everyone knows which transaction happened, the transaction history, and the order of the transactions, which ones happened first, and which ones happened. And so the miners, they first order the transactions, they place them in a block and broadcast them. The blocks get disseminated throughout the network, and then all of the peers take those blocks and take those transactions in those blocks and then execute them to update their local state databases to maintain this unspent transaction output database, which has a list of all the transactions that have all the transactions that are eligible for being inputs to subsequent transactions, ones that can be spent. So this is how in the Bitcoin network, all the nodes they can validate transactions and prevent double spending by maintaining this database. And so it's an order execute. So first the miners bundle the transactions into blocks. Those blocks establish a total order of all the transactions, and then the blocks are disseminated, and all the peers execute those transactions locally, and as part of that execution, they update their databases. Now, HyperLedger Fabric has actually 3 steps in the transaction lifecycle, so it's not order execute, but you now have execute, order, validate. And the way that works is when you deploy, a smart contract in a HyperLedger Fabric network, you specify in the smart contract some of the consensus rules. And what that means, specifically what that means is when you deploy the smart contract, you list you list a policy that specifies which other peers in the network need to validate the transaction in order for it to be valid. And so what ends up happening is there's a concept of endorsement peers. So when you create a smart contract and deploy it to the network, you say, these transactions are related to the smart contract are only valid if they receive endorsement from these peers. And so the client that issues a transaction will create a transaction and they'll send it to these endorsement peers to get endorsed. This is the execute step in the EOV architecture. So the endorsement peers, they receive this transaction, they execute the transaction locally. Now they don't update their databases yet because the transaction hasn't ended up in a block and the rest of the network hasn't received the transaction yet. So, but they execute it, they simulate the execution locally. So each endorser will receive this transaction, will simulate it locally, they'll execute the smart contract. The results of the execution of the smart contract is an update to the underlying database. And if the smart contract is executed successfully, none of the validation rules in the smart contract fail, then the endorser will add a signature and create an endorsement of that transaction and send it back to the client. And the client does that depending on the policy of the smart contract. So you could have a smart contract that says these 3 endorsers need to endorse. So for example, you could have Hossein, Julia, and Sam all need to endorse this transaction in order for it to be valid. And so if David created a new transaction and he's sending it to this smart contract that has this endorsement policy, then David would create the transaction and send it to Sam, Julia, and Hossein to execute. And we would execute it or simulate the execution. So we're not actually updating our databases yet, but we're determining what the updates would be if we were to. And if things look good, we add our signature and say, yep, this looks like a valid transaction, and we send those endorsements back to David. David gets these 3 endorsements, and that's the completion of the execute phase. And so now, if David wants to commit this transaction, meaning he wants the rest of the network the blockchain network to be updated with the results of the execution of this transaction, then he needs to have the transaction ordered. And the way he does that is he then takes this endorsed transaction, so the transaction that has the 3 signatures from Sam, Julia, and Hossein, and he's going to submit this to a service, and we'll describe the components of the service later in the session, but he submits it to an ordering service, which is then responsible for for placing the transaction in a block and establishing the order of this transaction among the entire history of previously received transactions. The ordering service, once it adds a transaction it creates a new block, bundles up a number of transactions. There's rules on how when it decides to create a block and how many transactions. You can specify how many transactions there should be in a block, or the maximum number of transactions in a block, or the maximum duration. You can wait for a block to be released. Those are all policies, ways you can configure your HyperLedger Fabric network. But at the end of the day, the ordering service will take this transaction that David has submitted, this endorsed transaction. It'll verify that, yep, all the endorsers have signed off on this and meets the endorsement policy for the smart contract. And then it will place the transaction in a block, where this block has a number of transactions that are pending to be committed or ordered. And then once it's ready to release the block, it'll take this block, this newly generated block, and it'll send it to all the peers. And then the ordering service also adds a signature as well. Only approved peers can perform this ordering type of function. So then all the peers receive this new block from the ordering service. The block contains this transaction and specifically it contains the updates to the underlying database in the transaction. This gets a little technical. I'm not sure we'll dive too deep, but I'll just say here and reference it later. There's a notion of a read and write set in the transaction, which basically means it's the data that the transaction reads from and the data that it writes to, the keys that it writes to and the data that it writes. There's a read and write set in each of these transactions, but basically it's the instructions on how to update the state database. All the peers receive this block. They go through all the transactions in this block. They do their own additional validation, make sure that it has the order signature that was endorsed, meets the endorsement policy, and then they update their state databases. They add the block to the end of their local blockchain data structures and update the database, and then the transaction lifecycle is complete. So the important thing is the peers at that last stage, the execute stage, the peers are only applying the updates to the state database. So they're not executing the smart contract yet. The only peers that actually execute the smart contract are at the very beginning of this process, those endorsement peers. And the result of the execution is the update to the database. And at this last phase, the validation phase, the peers are just applying these state updates and making sure that the state updates were endorsed. So this has a few implications as opposed to the traditional order execute architectures. So one is that not every peer needs to execute the entire smart contract. They're just applying, so only the endorsement peers need to. So not every peer needs to see the entire details of the smart contract. Only endorsement peers see that, where the endorsement peers are specified in a policy that's attached to the smart contract when you deploy the smart contract. Another implication of this architecture is that the non-endorsement peers, they don't, because they don't see the smart contract, they're not executing the smart contract, they're just updating the their underlying state database. What this means is theoretically you could have, in this type of architecture, you could support non-deterministic smart contracts. For example, just to give an example of this, if you had an endorsement policy that only required one signature, let's say just Hossein has to sign off on this, then Hossein could, and the smart contract, let's say generated a random number, it's not deterministic. Then David would send the transaction to Hossein. Hossein would execute the smart contract. It would generate a random number. Maybe it writes a random number to the database. Hossein sends David back the endorsement response and the result of executing the smart contract, that random number that he generated, and then David has all the signatures he needs. He doesn't need any other peers to validate it. So he can then take that transaction, submit it to the order of service, and then the order of service creates a new block, distributes the block to all the peers. Then all the peers just apply that update with that one random number. And that's an example of how an execute, order, validate architecture allows you to run, in some cases, non-deterministic smart contracts. Now, there's some questions of whether you actually would want to do this in practice, how that would be useful, but that's an example of how an EOV architecture is more flexible and supports a larger range of smart contracts than the traditional order execute architecture. Because in the order execute architecture, every validating peer is executing every smart contract, not just applying the updates, these read-write sets, but executing every step in the smart contract, not the result of the execution. So anyway, high level, HyperLedger Fabric has an EOV transaction model, which is different than all the other blockchain solutions out there, which are OE, order execute models, and that provides us some additional flexibility where you can now execute a larger range of smart contracts, which you can't in an OE type architecture. It has some implications regarding confidentiality, where only the endorsers need to see the smart contract code itself in order to endorse the transaction. And in some cases, it can have implications for scalability too, because not every peer and not every validating peer needs to execute the entire smart contract. Now, high level, let's go through some of the components of a HyperLedger Fabric blockchain network. So we talked about how there are endorsement peers. We also talked about validating peers. In general, this is just one type of. In general, it's just there are peers, and some of them do endorsements for some smart contracts, depending on the policy of the smart contract. But they all do validation, and they all maintain this state database that I mentioned, which is just the data that's available. It's the data that's read and written to by the smart contract. So in HyperLedger Fabric, the peers are written in the Go programming language. The state database is implemented as a key value store using level DB. This is just a database, a file-based database that sits on it's undistributed database. It's just a single key value store, file-based database that sits on a single server that came out of some work in Google. And so there's the peers. We talked about the database that the peers have, this level DB key value store database. HyperLedger Fabric also supports CouchDB as an alternative. In practice, we found the level DB performance to be way ahead of the CouchDB performance. And so practically speaking, although the CouchDB is a distributed database, it's JSON based, it can support richer queries. We found that in practice, it's only applicable for very low throughput, simple type of smart contracts and use cases. So we're almost always using the level DB database. There are blockchain clients. So I mentioned in the data life, the transaction example that we just walked through, how David is submitting a transaction. So David would be like, let's say, an Oracle and some other service off the blockchain network that's running a client. The client, or they call it software development kit and SDK, but what the client can do is it has a set of keys. So David would have some keys on his computer, and he'd be running software on his computer. that uses those keys to connect to the HyperLedger Fabric network and query the blockchain, create new transactions, submit those transactions to be endorsed according to the chain code policies, and then submitting the transaction to be ordered, verifying that the transaction was ordered in a block, and that would all be provided through this blockchain client or this SDK. So HyperLedger Fabric, there's SDKs in a few different languages. We use the one based on Go, but there's one for JavaScript, and also there's one in Python, and at one point there was one in Java. I'm not sure if that's still maintained. But anyway, they're clients. They're ways for off-chain services to create transactions and interact with the blockchain network. So we talked about the ordering service. So in practice, the ordering service, it's there's a few different. HyperLedger Fabric has been designed to be a very modular and generic type of system. So it's broken down into these different components that you can kind of rip out and replace with your own pieces if you want it. And the ordering service follows that style. So it has an API where you can plug in and use a few different types of orderers depending on the trust and scalability, availability requirements of your applications. So for example, if you're just doing a test network, there's what's called a solo order that just runs on a single server. It's just a Go program that's running on a single server that all the nodes, all the peers would be, or all the clients would be submitting their transactions to for ordering. That, that's going to have pretty high throughput, but it's also not available. It doesn't have high availability. It's a single point of failure. And there's a question if, depending on your application, if you have a bunch of sort of untrusted organizations on a single blockchain network, then there's a question of, okay, well, who's going to be the trusted third party to perform this ordering function? And so that led to the development of the Kafka-based ordering service. So Apache Kafka is a message queuing software that's it's an Apache, open source Apache project that has recently come into a huge amount of popularity and use in large enterprise systems. It's known for its high performance. Like LinkedIn is one of the biggest developers and users of Apache Kafka, but fundamentally it's a message queue type system where you have publishers and subscribers where you can publish messages on a queue or a topic, and subscribers then can pull those messages and read those messages from that topic. It's a little bit different from traditional message queues like RabbitMQ or JMX, for example, because Apache Kafka lets you read at arbitrary positions within the queue. So it's not always like a first in, first out, or last in, first out type of queue. In Apache Kafka, you can sort of scan forward and back in time to read messages in these queues. So anyway, the HyperLedger Fabric team has developed an ordering service that meets this ordering API that's built on Apache Kafka, and that's nice because it can be deployed in a high availability configuration. So for example, our products in AWS, when we deploy in the London data center, there's 3 availability zones in London, and we can configure the ordering service so that we have a replica running in each availability zone. And if a single availability zone gets disconnected from the network, it goes down, then the ordering service can continue uninterrupted and still process transactions and create blocks. So you no longer have the single point of failure requirement when using the Kafka ordering service. Now, without going into too many details of how Kafka works, but Kafka has its own consensus component that it uses, that it builds on. So it builds on another open source project called Apache Zookeeper, which was most commonly used in Hadoop and HDFS, the Hadoop file system. So it's been, Zookeeper provides consensus services. So when you're building, so there are many distributed applications that use Zookeeper in order to achieve consensus. It's one of the most battle-worn distributed systems. It's been around for a while, and it's been used in situations like, I know there's HDFS clusters that use Zookeeper at Facebook with tens of thousands of servers, and Apache Kafka builds on Zookeeper for its consensus. So when we deploy HyperLedger Fabric Network, we run Kafka brokers. We run 3 Kafka brokers, 1 in each availability zone. We run 3 Zookeeper instances, 1 in each availability zone as well. You can put the broker and the Zookeeper instance on the same machine to consolidate that, to make the configuration easier and to save money. That's an option. But the point is, Kafka, it's highly available. It builds on Zookeeper and performs consensus using Zookeeper. And the HyperLedger Fabric team has built an ordering service that uses Kafka to perform this ordering function, so that these ordering services are the ones for maintain the list of the most up-to-date blockchain, the most recent block, and they're responsible for delivering those blocks to peers that connect to the network. Now, that takes care of the single point of failure and scalability concerns. Apache Kafka is quite scalable. It's used, like I said, it's used to LinkedIn. But it doesn't address the trusted third party necessarily, because Apache Kafka it's crash fault tolerant, meaning it'll survive a Kafka broker going down and crashing, but it doesn't survive a malicious Kafka broker. So if someone, where Kafka starts to generate malicious messages and try to attack the network. So it's not Byzantine fault tolerance. That just means BFT just means a consensus protocol that's resilient to malicious actors, and there are these non-crash types of scenarios where it's not just the machine is crashing or turning off, it's actually a machine is starting to communicate on the network and send malicious packets, let's say. And so there is work to develop a Byzantine fault tolerant ordering service, and that's been in the works for a while. Costas at IBM has been leading a lot of that work, and there's one that IBM's working on called, based on their own, it's called SBFT protocol, their own Byzantine fault protocol, and there's another team at a university that built their Byzantine fault tolerant consensus protocol off a open source Java project called Smart. It's called the Smart BFT. These are still in earlier phases and more experimental. But if your application has these trust requirements where the organizations can't agree on that trusted third party, and so they each maybe want to run their own order, where they don't trust the other organizations to run their orders properly, then that's where you would need these Byzantine fault tolerant ordering services. And HyperLedger Fabric is designed in a way where you can rip out the ordering service and plug in a new one, and you don't have to change your smart contracts or any other part of the network or the clients or anything like that. So it's designed to be modular in that sense. Now, we talked about peers, we talked about the ordering service, the database, the client. So additional piece in HyperLedger Fabric component is there's a membership service. This is something that each organization would run. And the membership service is essentially a certificate authority, if you're familiar with what that is, but it's responsible for authenticating and providing, so making sure that people who come to the network belong to that organization. So, and it's also responsible for handing out the certificates or signing the certificates of the different participants. So all these transactions I mentioned have these signatures. They're also encrypted. All the communication between these different components is encrypted in transit, and the keys necessary to perform, to generate those signatures and perform that encryption have to be signed by the membership service. So each organization would run their own membership service provider, MSP, and and the clients, like we talked about David being an example client, on his computer, and he has his keys, he would have to go and get those keys signed by the Luther Systems membership service provider in order to generate it, in order to connect to the network and generate a transaction that will be processed by the network. So the MSPs are the gatekeepers. They perform this authentication. They're responsible for mapping the identities of the different participants and assigning them or signing their keys so that they can generate transactions that will be processed by the network. So every peer in the network has keys that have been signed by the respective membership service provider. Every client similarly has keys signed by the MSP, and the orderers, they all have keys as well that are signed by the membership service provider. And all the transactions are signed and encrypted using these keys. And at every step of the processing, the signatures are validated using these membership service provider, the public keys, using their public keys to make sure that they all have the right authentication to perform these operations. Now, in addition to the MSP, so we've talked about how the orderer broadcasts blocks. When the orderer creates a new block and receives these transactions, they'll broadcast that block and give the new block to all the peers, who then validate the transactions in that block in upper state databases, these level DB databases. And that's all well and good if all the peers are connected to the order and they're ready to receive that block and they're connected. But the entire HyperLedger Fabric system is designed to be fault tolerant. Like, nodes may come and go, they may disconnect from the network, new organizations may join the network, peers may crash, they may get restarted. And so it's not necessarily the case that a peer is ready to receive a block as soon as there's a new block, as soon as the order has a new block to give to the peer. And to handle that, HyperLedger Fabric has what's called a peer-to-peer gossip protocol. So this is very similar to how Bitcoin has a gossip protocol. So in Bitcoin, when you create a Bitcoin transaction, when you first connect to the Bitcoin network, you download the Bitcoin software. What you're going to do is you're going to connect to a random set of peers. So you'll have this set of 7 to 10 peers that are other computers on the Bitcoin network that have already connected to the Bitcoin network and downloaded the blockchain. And when you create a transaction in the Bitcoin network, you're going to take that transaction and broadcast it. You're just going to send it to all your peers. And then the peers take that transaction, they do some basic validation, and then they send it to all of their peers. And this type of communication pattern, this type of broadcast, peer-to-peer broadcast communication pattern, is what's called a gossip protocol. This is something that's not unique to Bitcoin. Many distributed systems have gossip protocols. There's a lot of mesh networking technologies that are entirely built around gossip protocols and this type of broadcast communication, a lot of routing protocols have to do broadcast and gossip in an intelligent way, so you can scale your network. But anyway, so when we talked about and described the HyperLedger Fabric architecture, it's different, right? So it's not the case that the client is taking a transaction and sending it to everyone they know. Like that's not how it works. The client takes their endorsed transaction and sends it to the order, and then the order hands it off to the different peers. So to handle cases where nodes, where peers may be offline, maybe they missed the block for some reason, they didn't receive the block, HyperLedger Fabric has added a gossip protocol, and that lets peers within an organization to receive blocks directly from their neighbors. So it's not a push-based protocol. It's a pull-based protocol. So the peers will have within an organization. This is at an organization level. The peers will periodically check in with their other peers in the organization. Will say, hey, what's the most recent block you have? What's the hash of that block? And it'll check what the peer has against what it has, and if there's something missing, then the peer will request the missing information from the other peer in this gossip-based way, this direct peer-to-peer-based way, instead of entirely relying on the ordering service to perform that function. And so this allows the peers to be able to be offline, not necessarily be connected to the ordering service. In some cases, you can configure HyperLedger Fabric so that not all the peers are connected to the ordering service. You can configure it so that only certain peers are connected, and the rest of the peers receive the blocks through this gossip-based protocol. So there's a notion of leader peers. So the leader peers are ones that are connected to the ordering service, and the leader peers will receive the block immediately from the ordering service, and then it'll hand them off to the other peers, the non-leaders, using the gossip protocol. Why would you do that? Well, again, in case the peer is offline, maybe it's not connected to the gossip protocol, but then also it can increase performance. So the more in Kafka, the more subscribers you have on a topic, the less performance you can achieve. So there's performance considerations. But the trade-off is now you have more of a delay for these blocks to propagate to the non-leader peers. Meaning non-leaders may not have the most up-to-date block. They're not going to have a different blockchain from the other peers in the network, but they may not have the most recent block. And that type of trade-off in blockchain architecture shows up all the time. So like in the Bitcoin network, it's not the case that all the Bitcoin nodes have the most recent block. There's a propagation delay, and that's why there's rules regarding confirmation times of transactions. So in general, if you're a vendor and you're accepting Bitcoin payments, you don't want to have. Well, first, you don't want to treat the transaction as being final without it first being confirmed in a block. But furthermore, typically you don't want to wait until one block. You want to wait 6 blocks in order for the blocks to propagate throughout the network, and in order to avoid certain blocks certain chains no longer being official, or the chains with the most work. There's sort of this forking that can happen. But generally speaking, there's a policy that as a vendor, you wouldn't treat a transaction as final until after 6 block confirmations, and peers in the Bitcoin network don't instantaneously all have the most recent blockchain. There's propagation delays using the gossip protocol in order for them to receive those blocks. And so, similarly in HyperLedger Fabric, by this notion of leader peers and the gossip protocol, you can have you can have non-leaders be behind. And when I say behind, I really mean like by a block or two, not more than that. And it's not like the non-leaders have a different blockchain. They're just not going to have the most up-to-date blocks. So at a high level, we covered a number of topics, but generally the different architecture differences between execute, order, validate, and order, execute from a scalability and transaction throughput standpoint. We talked about cryptography and the membership service provider, and we overviewed all the different components in a HyperLedger Fabric network, namely the peers, endorsement peers, leader peers, the ordering service, clients, membership service, and we also touched upon the consensus, how the ordering service provides consensus services, and in our case, we're building on Apache Kafka, which builds on Zookeeper for crash fault tolerant consensus, and we briefly dived into the gossip protocol. Thank you.
Thanks, Sam. I would only have one question, actually. So you talked about Kafka as the orderer, which uses Zookeeper. And what I didn't catch exactly was what Zookeeper was exactly.
Yeah, great. That's a great question. Zookeeper is a distributed system. So it's a piece of software that runs on multiple servers, and it provides consensus services. And what that means is you can think of it as a very simple database. It's a file. It's probably easier to think of it as a very simple file system, where Zookeeper will ensure that all the nodes in the Zookeeper network are up to date and see the same exact file system. So you can create a new file, you can write data to the file, and all the other nodes, Zookeeper performs consensus so that all the other nodes see the exact same file and are in agreement of that file. And it's a very general, you can think of as consensus as a service piece of software, and it's used by a number of different distributed systems. So I mentioned Kafka. Hadoop is a big data analytics service which builds on HDFS, and Hadoop and HDFS use Zookeeper to perform these consensus services and make sure that all the nodes are in agreement. So it's a building block to build distributed systems on top of that require consensus.
Okay, great, thanks. So thanks a lot for the session on HyperLedger. And next time we will speak about the Luther Enterprise Infrastructure Architecture. Thank you.